All right, let's start with our first reaction, alpha halogenation. So taking that alpha carbon and popping a halogen on it. Under acidic conditions, ketones and aldehydes undergo alpha halogenation. It works with Cl2, Br2, or I2. Again, no fluorine, please. Not going to be helpful. Notice this is under acidic conditions. We have a little bit of H3O plus. That bracket around it again just means it's catalytic amount. So H3O plus is not going to add things except for being able to use proton transfers. So acidic conditions also means enol is the reactive intermediate, right? We will not see reactive bases in this curved arrow mechanism. If we're in acidic conditions, just like before, we see positively charged things, not negatively charged things. Let's go ahead and walk through the mechanism. We're in an acid. What do acids do? They donate protons. We're going to see the enol formation, the tautomerization to the enol form first. So protonate that oxygen of the carbonyl. Then show the resonance. Notice the resonance arrow here. I don't need it to be in brackets, but I do need to see the resonance form. And then we'll take water to form the enol in a second proton transfer. That enol then goes into part 2 of this reaction, which is the actual nucleophilic attack to add on our bromine to the alpha position. Oxygen rolls its electrons down to reform the carbon-oxygen double bond, picks up a bromine onto the alpha carbon, kicking off the other bromine. Br minus is the only negative charge that we can see here because Br minus is such a stable anion. Hopefully we remember that and don't think weird thoughts about that, kicking off a leaving group of Br minus. And then we'll do a final cleanup of proton transfer, right? We used the acid and we're going to reform the acid as well. Beautiful. When unsymmetrical ketones are used, when we have two different alpha positions, I'll just call them alpha 1 and alpha 2, halogenation occurs faster at the more substituted carbon. And the reason for that is because the enol that forms is more stable when it's more substituted. And so the alpha position that would be more substituted gets to be major. Alpha halogenation provides a really great synthetic analysis for adding halogens, right? Whenever we can add a halogen to an organic molecule, we have opened up the world to us. Typically, we can see substitution occur, we can see elimination occur, anything that we had done in the sp3 carbon to leaving group range, right? Also, what's really great is we are going to see what we call alpha beta unsaturated ketones. Remember, if this is the alpha position, we can halogenate that alpha position and then do an E2 reaction where we make conjugated substances. That's awesome. We know that that is going to be a stable type of molecule when we have conjugation. That always is great. It also creates now a new pi bond between two carbons, which is extremely helpful. The most obvious E2 reagent that you probably will have seen is terbutoxide. All right, we do have the HVZ reaction that brominates the alpha carbon of a carboxylic acid. Now, alpha halogenation previously with acid catalyzed H3O plus and Br2 cannot work with carboxylic acids because of the actual acidic proton on the carboxylic acid functional group. So we do have a slight different reaction here. We do not need to go through the curved arrow mechanism. Just note that the only functional groups for our previous acid catalyzed reaction were aldehydes and ketones. If you have a carboxylic acid, you have to use the Helvell-Hord-Zielinski reaction, which is Br2 with PBr3. Again, PBr3 is a Lewis acid catalyst, all right? So it does slightly change our intermediate to an acid halide enol. But again, it's because we're avoiding the carboxylic acid functional group. We still put the bromine on the alpha carbon, right? So alpha carbon gets the bromine. Alpha halogenation can also be achieved under basic conditions. It just happens a little bit differently. Mechanistically, we go through a very similar reaction, except for we are forming an enolate. Right, so hydroxide is used with Br2. That hydroxide will deprotonate the alpha carbon. Again, this is an equilibrium reaction. We're not using a really, really strong base because we are promoting that enolate to react to add on the bromine at the alpha position. And that second step is what drives the reaction forward. Now, under basic conditions, polyhalogenation typically occurs. So if this was an exam question, I would expect you to halogenate every alpha position that we have. Because once the ketone is brominated once, it actually is a more stable enolate and it forms faster with one bromine and then two bromines, et cetera, right? So this is what we would expect for the product of base catalyzed halogenation. You find the alpha carbons, however many alpha protons there are, you pop a bromine on them. Under basic conditions, methyl ketones are converted to carboxylic acids. And that is because of using excess halogen and hydroxide. It's called the haloform reaction. And what actually is the intermediate that will form is a very, very good electron withdrawing group, CBr3, and then H3O plus will convert that to a carboxylic acid. Let's take a look at the haloform mechanism so that we can see the acyl substitution that occurs here. After all three alpha protons are replaced in our base substituted reaction, just like before, base catalyzed, the CBr3 acts as a good leaving group. And so hydroxide can come in, attack the carbon of the carbonyl in a pseudo chapter 20-ish style reaction. And then oxygen will roll its lone pairs back down after forming that tetrahedral intermediate and kick out the good leaving group, which is CBr3. Now, again, the resulting carboxylic acid is deprotonated, which even though this last step of kicking out the leaving group is an equilibrium reaction, it's the reaction of proton transfer between the leaving group and the carboxylic acid that drives the reaction to completion. This is a very, very good acid-base reaction. So that's also why we typically see H3O plus, an acid workup, used. Very reminiscent of chapter 20, if I might say. All right, so Br2Cl2 or I2 can be used with base catalyzed halogenation reactions as well. These are great ways to produce carboxylic acids from ketones. It works best if the other alpha carbon has no alpha protons though, because again, this is the Oprah reaction of halogenation, alpha halogenation under base catalyzed condition goes everywhere. You get a bromine, you get a bromine, you get a bromine. It's the Oprah reaction. So if you just want to convert to a carboxylic acid, be aware that this R group should have no alpha protons to best fit what the haloform reaction was intending.